So this would be my competency for 4.4, which is internal forces. So I've done some of the math right now. I got some of it done just because it's a lot of little stuff, but I'll walk through all of it. It's just a lot of like doing a little bit of math to figure out moments and stuff. So I just kind of did it beforehand, so we didn't have to take quite so long. So our goal was to find the internal forces on this beam 7 feet from A. So this is very similar to method of sections. So we start off with this red beam here. All the stuff in red was kind of what we had, and then we had all of our blue forces and distances. And then I found the orange stuff here, and we'll get to how I did that in a second. But so we need to find it 7 feet from here. So the first thing I did was I just went over, okay, 2, 3, 6, and then 7 will be right there. So we're gonna make a cut, and this is very similar to method of sections, where you're just gonna cut the beam into 2 pieces. That's kind of a way to think about it. You're sectioning the beam into cuts. So you'll do that, and then we'll draw our free body diagrams in a minute. But first, we want to just find our first step is to find our global equilibrium. So we need to find our AY and our BY. To find BY, I just sum the moments around A, which are equal to 0. We've got this force of 100, and that is negative. No, yeah, right? Yeah, sorry, that moment is negative. At 2 feet, 150 is also negative. At 4.5 feet, you have this moment right here, negative 200, and then you have BY acting at 9.5 feet. When you do all that math, you get 113.2 for BY, and then we need all the stuff going up to be equal to all the stuff going down. So you just add up your 100, your 150. Then I also made this, I guess I forgot to say that I made that a concentrated force. It's a rectangle, so it acts right in the middle. So that's at 1.5 feet. That's where that 4.5 came from. The 2, 3, 4.5. But it's just 5 times, it's just 50 times 3, which is what it's acting over to give you the force at that point. So yeah, you get BY, so now all your stuff going up needs to equal your stuff going down. So you sum all of this, and then you subtract 113, and you get 136.8 for AY. So now we can go to our, actually do our internal forces and take our cut. One thing that I need to talk about really quick here. So if we have a beam like this, say this is the right side of our beam, so this is this guy, you will have a normal force going out. So there's 3 forces you need to worry about. There's normal forces, there's shear forces, and there's moment forces. So normal force is, like if I was going to take the cap off of this marker, if I was going to either stretch or compress this beam. So basically force is like this. So if I'm taking the cap off, or if I'm putting the cap on this marker, that's what your normal force is. So that's what this is. And your normal force, so like for this right side, all of your forces are going to be on this end of the cut. You draw them at the cut. So if it's, just think about it as this section. That's what I'm going to kind of do this part off of. The next thing you're going to have is V, which is your shear force. So I just think about it like ripping a sheet of paper. So if I was going to take this marker, I'll have one hand going up, one hand going down, and just tear it in half. And that is, so on the right side is positive, on the left side it's negative. That's just how it kind of is to start. So I guess I say positive, negative. Going down on the left side, up on the right side. You just kind of do it a guess, honestly. It really doesn't, like there's no, you just kind of guess, and if you get a negative number, then you just need to flip it. And then we have our moment. Your moment is always going to be up, so towards the, like this side is going there, and this side is going there. Excuse me, sorry about that. So yeah, it's always going like around the beam to rotate it kind of away from the cut, like you were going to take it and break it vertically. So those are your 3 forces there that you want your foot. Your normal force, your shear force, and your moment force. So now I can add those to this guy. That's why I left them out, so I can explain that. So you have your normal, you have your shear, and you have your moment. And we're looking at this cut right here. So now we get to some of the math that we did, or that I did, I guess. So the first thing I did was I just drew I drew my free body diagram on both sides. I added all of my forces, and I drew all of this stuff, and then I'll find my moment, my shear, and my normal force, because those are the 3 internal forces happening in this beam at this point. And you can do this for any point on the beam. This was just the one that we were asked to find. So you draw those, just kind of get an idea of what they were doing and the positive directions for them. And then, so I started off on the right side actually, and I know that, so if I look at this, right, our normal force is the only thing in the x direction. We have this 200 and we have this 113, but there's nothing acting in this x direction because we have a moment. Well, that's not going to have anything to do with the normal force, that's the moment force. You have this, but that's a shear force, or that's, it's in the y. So our n is 0, our normal force, there's nothing compressing, or there's no compression or tension force on this beam. The next one is our shear. The only thing we have going up or down is our 113. So that's negative 113 because of this side. That's technically the positive. That's a little confusing, but it should be the same on both sides. So I think this is your positives and these are your negative directions, because you do everything off your left side usually. So that's why technically your positive shear force is down. It's kind of weird, but yeah. But you get a negative number there because it's, yeah. And then you have your moment. So we did the moment around the cut. You always want to do the moment around the cut because that's the force acting on that point. So if you think of a point right here, you have your negative 200, you have your 113 at 2.5, and then just use the dimensions from up here. If you go 7, the beam is 9.5, so that means there's 2.5 there. That's how long that is. And then you get 83 pound-feet for your moment. And it's positive going this way, counterclockwise, which makes sense because these are all negatives, so negative force directions. So then we move to this side, and your normal force, your shear force, and your moment force should all be the same on both sides. So I did it anyway just to prove that that's true. So the first thing is I sum my forces in the y to get my shear force. So I have my 136.8 here. It's my A of y. I've got the 100 force is negative. I've got the 150 force is negative. And then I have our shear force, which is also negative, and a negative direction. And then when you solve for all of that, you get negative 113.2 again, which is what we got. And then the next thing, our normal force again is 0. There's nothing else, there's nothing acting in this x direction other than our normal force. And to balance our normal force, like sum of our forces has to equal 0. Well, the sum of our forces in the x direction equals 0. And the only thing we have is our normal force, and that means our normal force equals 0. So that's just kind of the way you think about that. So sum the forces in the y, sum the force in the x, and now we need to sum our moments. So we have our moment force we're looking for, and we're always looking at it from the cut, so from a point here. So that's why everything is going to look a little weird distance-wise. So we got our 150 acting at 2.5 from this, because this is 1 over, and then 1 plus 1.5 is 2.5. Our 100 acting at 2.5, and another 2. Let's see. Yeah, that's acting at 5, 1, 4, 4, 5. Sorry, acting at 5. Yeah, 1, 2, 3, 4, 5. There we go. Okay, and then we have our 136.8 acting at 7, because this is 2.5. Whole thing is 9. So 2, 6, 7, 8, or 3, 6, 7. There we go. I promise I did do the math. That's why I did it all before, so I didn't have to count. We get 83 again for that one, just off for your moment. So that just shows you that as long as you don't round too much, the exact value should be the same or very, very, very close. I think this is like 82.6, and that one's maybe a little more like a little closer to 83, but for the most part, your forces should be the same on both sides. And as you can see, this side is a lot easier to solve for. So that's something where if you're asked for a problem like this, you want to find the easier side, probably the side with less things. This just has a lot going on. Not that it's difficult, there's just a lot more places that you can mess them up. But yeah, that's internal forces. So you always want to find your normal force, which is your force in the x, your shear force, which is your force in the y, and then your moment force, which is the rotational force. And you always sum your moments from the cut. But yeah, that's internal forces.